time constant of the circuit. Okay, it is the time taken by the response to reach 36.7 percentage of its initial value, or it is the time taken by the response to reach 63.4 percentage of its final value. See, for example, when you have a source free circuit, okay, initially you will have some initial value, your final value will be zero. Okay, so exactly at the time that is equal to the time constant, at it is equal to tau, your value will be 36 percentage of the initial value, okay, for a source free circuit. Okay, or otherwise if the circuit is consist of some source, okay, then at exactly at t is equal to tau, your value will be 63.4 percentage. Okay, so once if it is source free circuit, this is 36.7 percentage. If the circuit is with the source, then it is like 63.4 percentage of its final value, because when you have a source, most probably your capacitor or inductor at the initial stage will not have any energy. Okay, so we are trying to provide energy to the inductor or capacitor. Okay, in that process, again it will reach the final value, the energy or voltage or current across the voltage across the capacitor or current across the inductor will reach its final value. Okay, so at exactly at t is equal to tau, that value will be 63 percentage of its final value, because initially the value will be zero. Say for example, if this is with respect to initial value, okay, if you are having initial value, then it may be the source free circuit. Okay, so once if the inductor or capacitor is connected with the resistance, then the capacitor voltage or inductor current will decay like this. Okay, as the time progress, the energy inside the capacitor or inductor is getting decreased. Okay, so that's why the voltage or current in the circuit will get decreased. Finally it will reach zero, because the source free circuit will have zero value at a steady state. Okay, so it is getting discharging. Okay, so that means what, you are already charged your mobile, then now it is, now you are using your mobile, then it is like in a discharging state. Okay, you are not connected with the charger, now you are operating with the battery. Then what will happen, the charge inside the battery will decay like this. Okay, this is the example for discharge. Okay, that means the at t is equal to tau, the value will be e power minus 1, that means 36 percentage of the initial value. Okay, or otherwise initially your mobile is not having any charge, then you are charging your mobile, so again your charge will increase like this, then it will attain the steady state finally. Okay, so that time again this nature will get during the charging process. Okay, so once if the network is connected with the source, initially the element present in the network, that is either inductor or capacitor, it is not having any energy. So then we are providing the energy to the inductor or capacitor with the help of the independent sources. Then the capacitor voltage or inductor current will increase exponentially like this, then it will attain the steady state. Okay, then what is happening at t is equal to tau? So that is 1 minus e power minus 1, then that value is 63.4 percentage. That's why for time constant tau, we are having two different definition. One is 36 percentage of the initial value, and another one is 63 percentage of the final value. Okay, so in case of this, the value is getting decreased. In case of this, the value is getting increased. Okay, so next, with respect to only with respect to unit, we will have some relation, that is second is equal to second. That means tau is equal to tau. Okay, if it is a RL circuit, then tau we can write like L by R. Okay, for RC circuit, simply RC. Okay, then L divided by R, this R and C comes, then this is like resistance only. So this unit is ohm. Or if it is R square C, then it is like L, that means Henry. Okay, if it is L by R square, then it is only with C, that is Faraday. If it is RC by L, then it is 1 by resistance, that is mho. If it is L by C, this is resistance square, that means ohm square. If it is square root of L by C, then simply it is ohm. Okay, or otherwise if it is R square C divided by L, simply the value is 1. Okay, so this relation we can use with respect to only unit. Okay. Next, how to solve the problems related with the time constant. How to find out the time constant for the circuit. Okay, so this procedure is valid only for the first order circuit. Okay, so we cannot apply this procedure for the second order and third order circuit and all. Only for first order we can use this method. Okay, so in general, the time constant is the product of equivalent resistance in the circuit, equivalent capacitance in the circuit, or otherwise, if the circuit is having only single resistance and single capacitance, then it is RC, simply RC. Now remove the C equivalent, okay, because you may have a single C capacitor, or if there is more than one capacitor in series or in parallel, you can make it as a single capacitance, that is C equivalent. Then also remove the effect of the source, okay, independent voltage source. Okay, then if it is a voltage source, make it short circuit. If it is a current source, make it open circuit. Then find the R equivalent looking from the capacitor, because capacitor is already open. Okay, looking from the capacitor, find the R equivalent. Then finally we can find out what is tau, R equivalent and C equivalent. So now the problem is given 10 volt is connected with 1 kilo ohm and 2 microfarad and in parallel with 3 microfarad. Okay, the switch is closed at t is equal to 0. Exactly at t is equal to 0, the switch is closed. Now we are going to find out the time constant after t is equal to 0. Okay, so now first you find out the what is C equivalent. Now the capacitor, there are two capacitors, they are parallel to each other. Okay, then 2 in parallel with 3 will get 5 microfarad. Okay, then you remove that capacitor. Okay, then looking from this terminal, you find out the R equivalent, and before that, you just remove the effect of this source. That means you have to short circuit this source. Okay, you short circuit this, then you calculate the R equivalent. Now the R equivalent value is simply 1 kilo ohm. Okay, then the product of this two, 5 microfarad and 1 kilo ohm is 5 millisecond is the time constant of this circuit. Again, what is this time constant is telling? Okay, this time constant is 5 millisecond. Again, this time constant depends on R and C. It may be 5 millisecond or 5 microsecond or 5 second. It all depends on the values of the resistance and capacitance present in the circuit. This time constant is independent of the voltage source. Okay, so irrespective of the voltage, the time constant depends on the circuit parameter. So that means finally how fast your voltage is getting increased or decreased is decided by the component present in the network, but not by the source voltage, because you may have a wrong understanding. When the voltage is more, source voltage is more, it will take more time, or when the source voltage is less, it will take less time. Like that, you may have some wrong understanding, that and all not correct. So always how fast the circuit is working, it depends on what is the value of tau. Okay, if the tau is very small, then the circuit will be very fast. Okay, so if tau value is high, then it will be slow. That is the idea. So what tau is indicating, how fast or how slow you are reaching the steady state is decided by the resistance and capacitance value. Okay, present in the network, but not by the source voltage or current. Okay, where tau is the time constant of the circuit.